17th International Physics Olympiad 1986 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. Problem 1. Wave interference. A plane monochromatic light wave, wavelength lambda and frequency f, is incident normally on two identical narrow slits, separated by a distance d, as indicated in Figure 1.1. The light wave emerging at each slit is given, at a distance x in a direction theta at time t, by y equal a cosine 2 pi ft minus x over lambda, where the amplitude a is the same for both waves. Assume x is much larger than d. Question 1. Show that the two waves observed at an angle theta to a normal to the slits have a resultant amplitude a which can be obtained by adding two vectors, each having magnitude a, and each with an associated direction determined by the phase of the light wave. Verify geometrically, from the vector diagram, that a equal to a cosine theta, where beta equal pi over lambda d sine theta. Question 2. The double slit is replaced by a diffraction grating with n equally spaced slits. Adjacent slits being separated by a distance d. Use the vector method of adding amplitudes to show that the vector amplitudes, each of magnitude a, form a part of a regular polygon with vertices on a circle of radius are given by, are equal a over 2 sine beta. Deduce that the resultant amplitude is a sine n beta over sine beta, and obtain the resultant phase difference relative to that of the light from the slit at the edge of the grating. Question 3. Sketch, in the same graph, sine n beta and 1 over sine beta as a function of beta. On a separate graph show how the intensity of the resultant wave varies as a function of beta. Question 4. Determine the intensities of the principal intensity maxima. Question 5. Show that the number of principal maxima cannot exceed 2d over lambda plus 1. Question 6. Show that two wavelengths lambda and lambda plus delta lambda, where delta lambda much less than lambda, produce principal maxima with an angular separation given by delta theta equals n delta lambda over d cosine theta. Where n equals 0, 1, 2, etc. Calculate this angular separation for the sodium D lines for which lambda equals 589.0 nanometers, lambda plus delta lambda equals 589.6 nanometers, n equals 2, d equals 1.2 by 10 power negative 6 m. 17th International Physics Olympiad 1986 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. Problem 2. Seismic waves. Early this century a model of the Earth was proposed in which it was assumed to be a sphere of radius r consisting of a homogeneous isotropic solid mantle down to radius r(c). The core region within radius r(c) contained a liquid, Figure 2.1. The velocities of longitudinal and transverse seismic P and S waves respectively, are constant, Vp, and Vs within the mantle. In the core, longitudinal waves have a constant velocity Vcp less than Vp, and transverse waves are not propagated. An earthquake at point E on the surface of the Earth produces seismic waves that travel through the Earth and are observed by a surface observer who can set up his seismometer at any point X on the Earth's surface. The angular separation between E and X, 2 theta given by angle EOX where O is the center of the Earth. Question 1. Show that the seismic waves that travel through the mantle in a straight line will arrive at X at a time t. The travel time after the earthquake is given by t equal to 2r sine theta over v, where theta greater than r cosine r c over r, where v equal vp for the p waves and v equals vs for the s waves. Question 2. For some of the positions of X such that the seismic p waves arrive at the observer after 2 refractions at the mantle-core interface. Draw the path of such a seismic p wave. Obtain a relation between theta and I, the angle of incidence of the seismic p wave at the mantle-core interface, for p waves. Question 3. Using the data r equals 6,370 kilometers, RC equals 3,470 kilometers, VP equals 10.85 kilometers per second, VS equals 6.31 kilometers per second, VCP equals 9.02 kilometers per second, and the result obtained in question 2. Draw a graph of theta against I. Comment on the physical consequences of the form of this graph for observers stationed at different points on the Earth's surface. Sketch the variation of the travel time taken by the P and S waves as a function of theta between 0 and 90 degrees. Question 4. After an earthquake, an observer measures the time delay between the arrival of the S wave, following the P wave, as 2 minutes 11 seconds. Deduce the angular separation of the earthquake from the observer using the data given in question 3. Question 5. The observer in the previous measurement notices that some time after the arrival of the P and S waves there are 2 further recordings on the seismometer separated by a time interval of 6 minutes 37 seconds. Explain this result and verify that it is indeed associated with the angular separation determined in the previous section. 17th International Physics Olympiad 1986 year IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. Problem 3. Masses and springs. 3 particles, each of mass m, are in equilibrium and joined by unstretched massless springs, each, with Hooke's law spring constant k. They are constrained to move in a circular path as indicated in figure 3.1. Question 1. If each mass is displaced from equilibrium by small displacements u1, u2, and u3 respectively, write down the equation of motion for each mass. Question 2. Verify that the system has simple harmonic solutions of the form un equal an cosine omega t, with accelerations, negative omega square an, where for n equal 1, 2, 3 are constant amplitudes, and omega, the angular frequency, can have 3 possible values, omega 0 by square root from 3, omega 0 by square root from 3 and 0. Where omega 0 square equal k over m. Question 3. The system of alternate springs and masses is extended to n particles, each mass m is joined by springs to its neighboring masses. Initially the springs are unstretched and in equilibrium. Write down the equation of motion of the nth mass, n equal 1, 2 etc. till n, in terms of its displacement and those of the adjacent masses when the particles are displaced from equilibrium. Show that unt equal expression 1 are oscillatory solutions where s equal 1, 2, etc. till n, n equal 1, 2, etc. till n, and where phi is an arbitrary phase, providing the angular frequencies are given by omega s equal 2 omega 0 sine s pi over n. where AS are constant amplitudes independent of n. State the range of possible frequencies for a chain containing an infinite number of masses. Question 4. Determine the ratio UN over UN plus 1 for large N, in the two cases. Case A. Low-frequency solutions. Case B. Omega equal omega max, where omega max is the maximum frequency solution. Sketch typical graphs indicating the displacements of the particles against particle number along the chain at time t for cases A and B. Question 5. If one of the masses is replaced by a mass m' much less than m, estimate any major change one would expect to occur to the angular frequency distribution. Describe qualitatively the form of the frequency spectrum one would predict for a diatomic chain, with alternate masses m and m' on the basis of the previous result. Reminder. Take in account next trigonometry formulas.